All right, everyone. Let me know if you can hear me. I was muted for a little bit just to let some more people join in. But I think now that's around like 1:02, we can go ahead and get started. And we can start with the presentation. I think there's a little bit of delay, so I'll give it like as soon as I get a few confirmations that I can actually be heard. Okay, cool. All right. So today, what my presentation is going to be on is I'm going to be talking about quantum computing. I'll start off with a little bit of introduction. So, 1 second. So, quantum computing. So, before we get into quantum computing, I just want to give a quick disclaimer. We'll put this before all of our presentations this summer, but it's just saying that we're not really experts in the fields we're talking about. We're really passionate about the fields. We want to learn more information about them, but we're not experts about them. So, if there's any information that's incorrect, please feel free to reach out to us and tell us like about things that are wrong. And we're trying our best to make sure everything is as factual as possible, but we might get some things wrong along the way. So a little bit about me. I'm currently a rising senior at Georgia Tech. I'm starting my master's in the fall. And I've been working in the software engineering industry for a little while now, and I've been working forward that in the future as well. So what we're going to be talking about today is generally about quantum computing, giving you an introduction to the field, what it's about, and some of the applications about it. Now, I know that quantum computing can sound sort of intimidating. You might think it's something that maybe like research scientists at NASA only can work on, or really sort of involved scientists with PhDs and lots of years in the field. And that might be true when it comes to actually like working on research in the field. But today I'm going to be just giving you an understanding about some of the fundamentals of how quantum computing works, give you some ideas about what it means when people talk about quantum computing, and give you a little bit of insight so that if you want to move forward and work on this field in the future, or even read more about it on Wikipedia or other places as well, you have a good starting point for your understanding about it. And as always, if you have any questions, please feel free to put them in the chat. I'll be checking the chat intermittently throughout the presentation. And also at the end of the presentation, I'll leave time for questions as well. So the first thing we're going to get started is, what is quantum computing? So quantum computing, or quantum sort of science fields in general, are branches of physics and science that study the behavior of matter and energy at atomic or subatomic levels. So when you're thinking about planes or ants, all of them follow like a typical set of physics rules. Maybe you've heard of Newton's laws of motion, things of that nature as well. All these sort of like large scale objects, planes, ants, humans, we all follow a general set of physics rules or science behaviors. But when you get to the subatomic level or the atomic level, things that are so small that they're the fundamental building block of everything around you, the actual rules of physics and the behavior of matter and energy begins to change. And quantum computing is a field that leverages these scientific principles to build powerful computers that solve complex problems faster and more efficiently than typical computers like the one you're probably seeing this on right now. And a quantum computer is a machine that performs calculations based on these quantum mechanics and quantum physics rules. We'll talk more about this later, but quantum computers operate in qubits rather than the classical bit system. And one of the big things about quantum computing, or the two big things, are that quantum computers, even the sort of introductory beginner quantum computers that we have nowadays, at the initial stages of the field, are around 100 million times faster than the most sophisticated supercomputers at certain problems. Not at generically like overall, but in certain like problems, certain algorithms, certain processes, they can operate almost 100 million times faster, and they're only just getting started. And they also must be kept at a very low temperature. We'll talk more about that afterwards as well. So what is quantum computing in general? So quantum computing follows a science based on atoms and particles, like we were mentioning before. And the theoretical part of quantum computing, which is like the quantum physics side of things, has been developed substantially. It's been a field of research ever since like Albert Einstein, and it's been moving forward ever since then. But the practical implementation, actually making quantum computers and doing stuff with that research and science, is still a big problem. And the reason that we want to solve that problem is because these computers use a fraction of the energy compared to classic computers, and they handle operations at speeds that are hundreds, millions, or hundreds of millions times faster than classical computers. So if they're cheaper, I mean, if they use less energy to operate and can do much more with that energy, that's obviously a good field we want to be able to research in, especially moving forward towards the future. So a quantum computer uses the main sort of properties to perform computations. We'll talk more about these properties as we come up in next slides, but the properties are generally superposition, entanglement, interference. Don't worry if you don't know what these means. We'll go more into them in the future. But quantum computers are mainly used in research lab nowadays. It's too early to have one in every home. And in fact, most countries in the world don't even have them. They're basically concentrated in a few key high research fields or high research countries. However, you can have access to these quantum computers through cloud services that we'll also talk more about in the future. And there's a lot of big companies working on these quantum computer fields, stuff like IBM, Google, Microsoft, and Honeywell are spending a lot in this field. And it's going to be a big market as the research is only just getting started and the computers are only going to keep getting better and better and better. So we're going to talk a little bit about what are some of the fundamental principles of quantum computing, starting off with bits and qubits. So what is a bit? A bit is something that is present in sort of any computing medium, whether you're talking about, like the computer you're watching this on, maybe the phone you're watching this on, everything runs on bits, which are called binary digits. And these binary digits are either zeros or ones. I'm sure you've seen in some sort of like hacker movie or things like that, people always mention the zeros and the ones. It's because that's what computers run on. They take everything, they process and store everything they handle, everything the computer in front of you is handling is stored in two states, 0 and 1. They're called bits. And they have two possible states. It can be either 0 or 1. And that's the only options they have. These bits make up bytes, which then make up the kilobytes, megabytes, gigabytes that you're so familiar with and that you know in terms of storage. So you might be wondering, well, how is everything on my computer stored into 0 or 1? That doesn't really make sense. I have like colors on my screen, I have text on my screen, I have buttons. How is it all stored in terms of zeros and ones? So zeros and ones form like binary numbers or binary representations of things. Binary meaning two, like twofold. And so 0 and 1 are the two sort of states it can be in. And using these binary representations, we've set up a system that can encode stuff like letters, like the alphabet letter for A is encoded as that binary number. You can code numbers in them, obviously, because you can just switch bits on and on and off and represent numbers as powers of 2 rather than powers of 10. If you can represent letters, you can represent words by just putting one letter after the other after the other. You can also represent colors because colors are just numbers in some way. They're saying how intense do you want the red light, the green light, or the blue light in RGB sort of situations. And based on how powerful the red light, the green light, and the blue light are on an LED or on a light, you can create an infinite number of colors as a result of that. So orange is represented as certain RGB values, and those red, green, and blue values can all be represented as numbers, and therefore be represented in binary as well. So everything in the computer is represented in some way through binary. And in particular, ASCII is the name of the bit representation for text, which is used then throughout a lot of other things, since text can be used to represent a whole plethora of information as well. So now, what we talked about before is quantum computers don't exactly use the same bits as computers do. So typical classic computers, like the one you're using, use classic bits, which are the binary system. Things are either 0 or 1. Qubits, on the other hand, are what quantum computers use, and they can be in either of the two states. It can be 0 or 1 until they're measured. And we'll talk more about that property as we move forward. But this sort of representation of them, this spherical representation is called a block sphere. And it's a useful tool to visualize qubit states and quantum operations as well. So this representation of qubits shows that they can exist simultaneously in both the 0 and 1 states. They're unlimited in the same way the computer, like classical bits are, where they're either 0 or 1. They can be both 0 and 1 at the same time, and we don't know what state they're in. And the representation we have here, this bracket notation, is represented by direct notation, or sometimes also called bracket notation. And you don't need to know too much about that, but just know that this is, if you ever see this representation, it's probably talking about qubits or some sort of quantum science field as well. So more about what are qubits. So when you think about particles and matter in the world around you, typically you have large objects, let's say like the chair, the computer, like the table your computer is on right now. Those are made up of larger sort of objects. You can consider them matter. The table itself that you're like probably watching this on, or chair that you're sitting on, is made up of molecules. These molecules then can be split up into atoms, and then atoms have particles within them as well. The further down the sort of hierarchy you go, the smaller and smaller these items go, often by scales of thousands or millions. And then also the rules of physics begin to change once you go from atoms to electrons to protons and neutrons, and the stuff that builds them up as well. And that's where the field of quantum science comes into play. And many different physical objects can be used as qubits, and these can be these sort of subatomic particles like atoms, ions, photons, and electrons. The main differences between quantum computing and classical computing, before we go much more into it, is in quantum computing, information is stored in qubits that can be either 0 or 1 simultaneously. We're dealing with these small-scale subatomic particles, and power increases quite dramatically with the number of qubits. So the more and more qubits you add, and we'll talk more about this later, you can exponentially do harder and harder problems faster and faster. And since things can be both 0 and 1 simultaneously, you can do much faster data processing. So you can do stuff with multiple things at the same time. But there's a lot of error that comes with that. And classical computing is stuff that's bits that are either 0 or 1. You have transistors, capacitors, these sort of circuit components to make up your computers. And it's a lot slower, so things need to be done one by one by one. It's difficult to do things in parallel. But there's low error rates. Like you never really expect that when you do 1 + 1 on a calculator or computer, that's going to error out. You just expect your computer to work the way that it does. So why do we even need these quantum computers? Obviously, they're really fast, but if they're so difficult to make and they're only used for specialized tasks, why do we need them? Well, because some of these specialized tasks are very important. And supercomputers meaning very, very powerful computers we have nowadays, are not enough to solve these complex problems. And for these complex problems, it can take quite a while, often the scale of hundreds of thousands of years. And they don't have the memory to hold the number of combinations that these real-world problems have. And another thing they need to know before, like you go more into quantum computing, is the idea of quantum supremacy. Quantum supremacy, also known as like a quantum advantage, is the idea that there is going to be a point in which a quantum sort of computer, a quantum device, can solve a problem that no classical computer can solve in a feasible amount of time. And that's the point where we're going to say there's quantum supremacy, which means that quantum computers are provably superior to normal classic computers. Google sort of claimed this quantum supremacy with the computer that came out in 2019, but the usefulness of the problem they solve, and it's a very niche use case, it's often very highly debated. Typically, we refer to quantum supremacy nowadays as just which company has the best and most powerful supercomputer. We say they have quantum supremacy. So now we're going to talk more about the properties of quantum computing. So what actually are some of the physics to science principles behind quantum physics and quantum computing as well? For that, let me check for any questions. What are the complex problems computers solving? I'll talk more about that as we go forward, but I'll keep that in mind. If there's any more questions on that end, I'll answer them after as well. So in terms of properties of quantum behavior, the first one is superposition. So superposition essentially is the property of the qubits being in both 0 and 1 at the same time. So let's say you're flipping a coin. In a typical like classical situation, you flip a coin, and when a coin lands, you expect it to be either heads or tails. You know for a fact when the coin lands on the ground that when you look at it, it's going to either have heads facing up or tails facing up. That's pretty clear. But in the quantum world, a qubit or a quantum bit can be a mix of both heads and tails at the same time. It's like flipping a coin, and when it lands, you actually don't know what side the coin is until you observe it. You say, oh, it's either heads or tails. And it's not just saying that it's somewhere halfway between 0 and 1. It's a new state where it exists in both of these possibilities, maybe more 0, higher probability than 0 than 1. But it exists in multiple possibilities simultaneously. And this ability to be in multiple states at once is what gives quantum computers potential power. They can explore many possible solutions to the problem at once rather than trying to solve it one at a time, like a typical computer does. And then another thing to keep in mind is measurement collapses. So what this means is, let's say you flip a coin and you do the thing where you flip a coin and you put your hand over it. That's what people typically do when they're flipping a coin. Now, when you flip that coin and you put your hand over it, you don't know if that coin was a zero, you don't know if that coin was a heads or a tails until you lift up your hand and you see it there. So in that, I guess in that sort of like contrived example, you can say that the coin is both heads and tails until you lift up your hand and you see that, oh, I flipped the heads, or oh, I flipped the tails. That's sort of a similar situation, if you want to think about it, to the way that measurement collapses work. When you have these qubits that are both 0 and 1, and you measure them, once you go with the act of measuring them, now they're definitively either 0 or 1, and they lose that superposition property. And this allows them to do complex calculations much faster than classical computers. The physics behind that is something that you have to dive a lot deeper into the research for, but in general principle, this is what superposition means. So a good example, of the most popular example of this superposition, is with an experiment called Schrodinger's cat. So we can think of Schrodinger's cat as this qubit that we're talking about. So this is a famous physicist. His name was Erwin Schrödinger, and this is his thought experiment. So let's say you have a cat in a box, and there's also poison within the box. This poison has a 50% chance of killing the cat within a certain amount of time. So you put the cat in the box, and you put this poison in there as well. Keep in mind, this is a completely fictional scenario. This was never actually tested. It's just a thought experiment. So you put the cat in the box, you put the poison in the box, and so now the question is, can you know if the cat will be alive or not alive before you open that box? Obviously, once you open the box, it's easy to tell. While the box is closed, do you have any knowledge about that situation? And the answer is no, because while the box is closed, the cat is both dead and alive until you open it. That's the sort of quantum state we're talking about. When you're looking at a qubit, it's both 0 and 1 until you go through with the act of observing it, and then you're able to see which side is on. It's sort of a paradoxical thing. It's tough to sort of wrap your mind around, but this is the best example that you can think of when thinking about things in the quantum state. So just the act of opening up the box and seeing the cat changes the state of the cat being both dead and alive to either or. It either is dead or it is alive. Without observation, the cat's in both states. But as soon as you observe it, then it's no longer in both states. And does this, like, you might think this is sort of like a fake scenario. It's contrived. There's no way this really happens. When you look at the science and look at the physics of the quantum realm, things that are atoms and smaller than atoms, this is actually a basic nature of quantum objects, and something that we've actually definitively observed. So what is the advantages of the superposition property? Why do we sort of care about this? So let's say you want to process about 9 petabytes of data. This is an insanely large amount of data. This is 1 petabyte around 1,000 terabytes, which that itself, each terabyte is 1,000 gigabytes. Imagine how much storage that takes up. So let's say you want to process about 9 petabytes of data, like all the YouTube videos that are uploaded over the last 10 years. The amount of time it takes to process all that data depends significantly on the computational power of the device you're on. Some high-end laptop maybe takes several months to several years. The supercomputers might take days to a week to accomplish that problem. But a quantum computer might take only minutes to hours. And that's because since you're able to do things in parallel, since these qubits are both zeros and ones, you're able to do multiple operations at the same time. And only once you observe them are you able to actually get your output out of it. So the next sort of property of quantum behavior is entanglement. So what is entanglement? Entanglement talks about electrons, or sort of these quantum particles. In a magnetic field or within sort of an atom, an electron can exist of one or two spin states. It could be spin up or spin down. Just think of these. You might not have to know the physics behind it. You can just know that an electron can either be spin up or spin down. Before you measure it, like the qubits we were talking about before, the electron has a probability of being in either state. And so maybe let's say a 25% chance of being spin up or 75% chance of being spin down. But as soon as you measure it, the electron spin state is determined to be either up or down. It's like the Schrodinger's cat example. Once you open the box, You know exactly what state it's in. Entanglement means the sort of joining of two particles. And what it allows you to do is it allows you to take advantage of the superposition property we talked about before to make two particles into a single system. And they become so correlated that the properties of one particle affect the properties of another. So essentially what this is saying is it's saying that once you're able to measure and observe the properties of one of these particles, then across any distance, that other particle, you're able to know the properties of that as well without having directly observed it. And it gives these qubits more computing power because it allows you to add more to the system because you can connect them together the same way you connect sort of circuit components together in a normal computer. And this interaction seems to be faster than the speed of light, which is a very highly debated and highly researched physics problem as well. And people have actually done groundbreaking work in this field and actually been able to accomplish these sort of quantum entanglement in real life as well. In 2022, there was a Nobel Prize for Physics that was awarded to Elaine Aspect, Clauser, and Zellinger for their pioneering experiments working in this entanglement field. So, like the superposition example, I'm going to give an analogy to help sort of simplify what entanglement means. Let's say you have a pair of shoes. We call them some sort of magical quantum shoes. Shoes obviously come in pairs. So let's say you take the left shoe and you put it in one box, and you keep the right shoe in another box. And then let's say you shuffle these boxes up. Some friend shuffles the boxes up, and you have no idea how they shuffled it, which shoes are in which box, completely unmarked. And you have just now two shoes, a left shoe and a right shoe, in completely randomized boxes. So now you have an entangled system. And you might be thinking, oh, why do you have an entangled system? So shoes come in pairs. You have a left shoe and a right shoe. Now let's say the person who has the left shoe walks 100 miles walks like a couple thousand miles from New York to California. And let's say the guy who has the right shoe walks all the way from the US to like London or something like that. So now you have a pair of shoes. One shoe is in London, one shoe is in California. As soon as a person in California opens their shoebox and sees that they have the left shoe, you know immediately that the person in London has the left shoe. So as soon as one person has one pair of the shoes, the other person, regardless of the distance, regardless of how far they are, instantaneously knows which one of the shoes that they have. And that's what entanglement sort of means. It means the ability to have two particles that as soon as you observe one property of one of them, regardless of the distance, regardless of how far it is, you instantaneously know the property of the other particle. And that's what entanglement is. And they've done experiments with this as well, where they were able to actually entangle particles and send and receive information from over 7,600 kilometers away through the use of satellites. And the actual physics about this experiment, I won't go into, so it's very sort of in-depth research. It's a lot of physics, a lot of research in the field. But just know that they're able to maintain this connection through space using satellites. And since there's no like cables you have to lay across, there's no like land fiber cables you have to put across. There's just like you communicating to the satellite, communicating to the other person on the other end. It's around 1 million times or 10 million times more efficient than using optical cables. Because if you had to lay a cable from one side to 10,000 kilometers away to the other side, it takes a lot of time, it takes a lot of money, it takes a lot of energy to do as well. But through quantum entanglement, they're able to do this sort of communication almost instantaneously. In the future, you can have sort of quantum internet, you can have ultra secure communication networks, you can have instantaneous communication with people all across the globe with a much more energy efficient way as well. So what does this entanglement sort of provide? As you mentioned before, it lets you do an exponential increase in processing power. So each additional qubit you can entangle and store more and more information, store more and more memory. And it allows you to do parallel processing as well by saying that as soon as you observe a property of one, you observe a property of another. So this entanglement property is very, very powerful, has a lot of potential, but large-scale sort of quantum computers are still in development. You saw that the Nobel Prize in Physics that was awarded for this was only awarded in 2022. It's a very recent field. It's a very difficult field. And and the full realization of the potential of these sort of computers is still like a significant engineering and still a significant research and science problem. So we're going to talk a little bit more about qubits. So let's say we're talking about the sort of exponential increase in processing power. What does that really mean? Let's say you have two qubits that are entangled. You have this top left one and the top right one that is pair decided. The left one could be in the state of either 0 or 1, and the right one could be in the state of either 0 or 1. Now combined, they could store 4 different potential pieces of information. Either can be 0 and 0, 0 and 1, 1 and 0, or 1 and 1. If you add another qubit into that scenario, you now go from 4 to having 8 of them. You add 4 of them, now you have 16. The more and more qubits you add, each new qubit that you add exponentially increases the amount of information that you can store. And that exponential increase is 2 to the power of whatever amount of qubits you have. So 1, 2, and 3 is 2, 4, 8. You get to 16. And as I'm sure you know from like exponentiation, just the more and more qubits that you begin to add, the larger the qubits get, becomes the rate of growth of the amount of information you're able to store sort of exponentially increases and jumps to the millions or the billions very, very, very quickly. So what's sort of like a practical application of this? So let's say you have a maze. The left, let's say, is a classical example of a maze. If you're trying to solve a maze, or if you're trying to get a computer to solve a maze, what it'll probably do is it'll walk around the maze and encounter every single possible path. It'll start at where it says B. It'll go straight, hit a wall. All right, cool. Left, hit a wall. All right, right, left, continue going right and left. And as soon as every time it hits a wall, it has to go back and backtrack its progress. So it has to go straight up, keep hitting walls, and essentially has to hit almost every single wall on the way to its output before it's able to find the exit. And as you can see from like the top right part of the maze as well, you're missing out on a lot of efficiency like advantages by having to go down that entire dead end path and go all the way back, and go down an entirely other dead end path and go all the way back. And it's very inefficient to do this in terms of a classical computer method. Obviously, there's better algorithms for it, but still very inefficient. If you look at the right, which is sort of a quantum simulation of what a quantum computer would handle in this situation, you can see that it's able to take multiple paths at once. It's not able to just say, okay, I have to go down every dead end path. It's saying, okay, I can split the processing and go down the dead end path on this side. And I know that, oh, this is going to be a dead end. I can entangle that back to a previous qubit, send the information. I just don't have to go down that path anymore. And that way, it's able to avoid exploring paths multiple times, provide a much quicker output to the answer, much quicker answer to the problem they're facing with it. This is possible because of superposition and entanglement, allowing this sort of parallel computation. So what's another property? So far we've had superposition and entanglement. The next property that we're going to talk about is interference. Let me see. Oh, someone had a question about this one. In the Q maze, why didn't it go left where the wall was? That can also be one possibility. Which hurts. Oh, so it does. So are you talking about like the top left part of them? So the top left part of the maze is just, let's say that there was sort of imagination of the maze solving scenario. We're saying in this sort of simulated situation, let's say the path that the maze took was, let's say the path that the maze took avoided the top left corner. Even if it did take the top left corner, it would have had to backtrack in the original example. And in the quantum example, it would have sent one pathway that way and one pathway to the right. So while it could have gone to that top left corner, this is just sort of a simplification of it. It's not like an exhaustive example. Same thing with the bottom right corner as well, and the B versus the Q. Hopefully that answers the question. So the next property, so we talked about superposition, which is the ability for a qubit to be both 0 and 1 at the same time. We talked about entanglement, which means two qubits can be sort of connected with each other, and information about one can share information about the other. And the third property we're going to talk about is interference. So interference is like a fundamental phenomenon in quantum mechanics, and it comes from the wave-like nature. It might be tough to think about this, but some of the particles like photons and electrons act as waves. Think about like waves in the ocean if you want to think about it like that. So when a quantum particle is in a superposition, we mean that it's in multiple states at once. These states can interfere with each other, leading to either constructive or deconstructive or destructive interference. So let's say two waves hit each other and they're both going towards the same direction. If you have like one wave that's kind of small, and another wave that's very large, but they're both heading in the same direction, the smaller wave is going to catch up with the bigger wave and lead to an even larger wave. Let's say a 10-foot wave and a 20-foot wave. Maybe they could form a 25-foot or a 30-foot wave. That's constructive interference because it's constructing an even greater sort of amplitude or even greater wave. However, the opposite is also possible. Let's say you have a 20-foot wave that's going away from the shore, and a 10-foot wave that's going into the shore. They can collide, and the resulting wave could be much shorter than the sum of both of them. Obviously, waves is not just talking about waves at the ocean. They're talking about waves in terms of a physics perspective. But if you're not familiar with the physics perspective, it's sort of the best example that I can give. Destructive. So these sort of graphs provide you an example of what constructive and deconstructive interference is. So the bottom two graphs showcase the two different waves. On the bottom, you can see here that these two waves are in the same direction. The frequency and their amplitude and their period match up. So when the two waves combine, they create an even larger wave that's bigger than the two of them. However, when you have destructive interference, like I can see when this one goes down, the other one peaks. When this one peaks, the other one goes down. That destructive interference leads to a straight line. It destroys both of the waves and leads to a wave that's sort of the subtraction of both of them you can think about. They cancel out. This is a similar principle to like noise canceling headphones and things of that nature as well, because what noise canceling headphones do is they output noise from the headphones themselves to cancel out the noise in your surrounding atmosphere, and that's how they work, or a basic version of how they work. And this is using quantum computing to cancel unwanted states and improves the accuracy of the calculations. So what's sort of an example of like scenario in which this works? So let's say you have this is an experiment that was set up. Let's see, you have a photon detector, a photon emitter, and a photon detector. So a photon is a particle of light. You don't have to know exactly what that means. You can think of it just as like a small particle. And in this experiment, you have a photon emitter on the right that's shooting photons at this thing called a beam splitter. And this beam splitter splits a beam of light into two or more beams. So when you shoot a photon from the left side of the screen into the device, into that beam splitter, it chooses a random path for that photon to go in. Maybe it's a 50% chance to go into the top detector, or 50% chance of being transmitted through the actual beam splitter into the photon detector on the other side. But here comes like the sort of weirdness of quantum mechanics. Here, you can actually manipulate the probabilities to get the desired outcome. And that's what interference is used for. Here, let's say you want the photon emitter and the photon detector to be connected. You want that every time I shoot a photon from that emitter on the bottom left, it'll always go to the top left of the screen, always go to that detector. You can actually take advantage of this interference mechanic to only shoot. So let's say the beam could split into like this top direction or this left direction. Here you can say, all right, this is not a direction that I want to go in. I'm going to use destructive interference to cancel out that wave. Let's say this right side is the side I do want to go on. I'm going to use constructive interference to amplify it. And by destroying and amplifying at certain intervals or certain parts of the photon's path, you can ensure that it'll go down the right path that you want it to go down. And the last sort of property that we're talking about, so we have superposition, entanglement, and interference. The last one we're going to talk about is decoherence. And decoherence refers to the loss of the sort of quantum properties in the system. So what do we really mean by that? It's essentially saying let's say we had that shoe example where both people, one person in California, one person in London, had no idea which shoe they had. As soon as they opened and observed that system, it was no longer quantum. It lost its quantum properties. It wasn't in both states at the same time. It's either one or the other. And that's what quantum decoherence is about. It's about losing the quantum properties of your system. And this can be due to a large amount of things. It could be due to like observing the system yourself. It can be due to environmental interaction with the system, any sort of interaction with a quantum system and its environment surrounding it causes it to lose its quantum properties. It's a very delicate system. And it's the fundamental challenge in scaling quantum computers is this sort of decoherence thing. It's every small little thing. It could be a speck of dust. It could be temperature. It could be heat. It could be air. It could be sound. Any sort of outside interference could cause these quantum computers to completely fail and cause all of them to lose quantum properties. And it's very difficult to build quantum computers because of this decoherence property. And it essentially removes the quantum properties in qubits and just turns them into normal bits, which makes quantum computers no longer effective, if effective at all. And currently, the issue is that we have a high rate of decoherence. We have a high rate of errors within our quantum computers. And with that high rate of errors, we lose our ability to maintain these quantum states and lose our ability to run the computer for a large amount of time. And that's sort of the biggest issue within quantum computers today. That's why we can't scale them that high. So what are some of the ways we're thinking about handling it? Now, this is obviously a very, very new and up-and-coming field of research, so I'm not going to have all the information about it. One of the primary ways that we go about it is this thing called quantum error correction. Quantum error correction uses these temporary qubits called ancilla qubits in some examples, and it uses them to detect and correct errors. So the way that this works is, let's say you have like this qubit here that carries information. We have this ancilla qubit over here that we entangle with this information carrying one. And so what that does is any errors in this original qubit, let's say this is supposed to be like both a 0 and a 1, but it goes through decoherence and it's observed and it loses that sort of capability. Obviously, since this and this are entangled, and any errors in the original qubit will affect this ancilla qubit that we've added. And we can always measure this ancilla qubit to reveal which errors occurred and how they occur. And we can also apply corrections to ancilla qubits since they are entangled to restore the original state of the information carrying qubit. So using this separate ancilla qubit, what we're able to do is identify errors and restore our original qubits to their correct state through corrective operations. But obviously, if for every qubit we need an ancilla qubit, or maybe we need more than one ancilla qubit as well, one of the challenges that arises is that we want more information carrying qubits in the system. We want more information or actual like useful qubits in the system. But if for each one of those useful qubits, we need to have 1 or 2 ancilla qubits, the cost and the scale goes exponentially up as we try to increase the amount of qubits. And also complexity of the system as well. Another thing is to try to suppress decoherence. And this is done by trying to minimize the interaction between the quantum system and its environment. The way we do this is to cooling the system to very low temperatures. I'll show more about that later. Isolate it from the environment, keep it in sterile rooms the same way you would kind of consider like hospital emergency rooms are very sterile. They keep it clean. They don't want any germs to be in there. And sometimes we try to avoid decoherence altogether by designing quantum algorithms and quantum systems that are just less sensitive to decoherence. Things that can handle more errors being thrown and not fail. So the quantum error correction is about stopping errors from happening. Suppressing decoherence is about stopping decoherence from happening. And avoiding decoherence is about just creating algorithms that don't care about decoherence or not in general. You can do this by the actual building of the system or by using better algorithms as well. Go check any questions. So how does it remove the quantum properties? So decoherence removes the quantum properties by, I guess you could say, observing the system. Let's say like some particle from the outside interacts with it, or heat interacts with the system, or cool interacts with the system, heat or sound or anything like that interacts with the system. That counts as observations. It's interacting with the qubit or interacting with like the electron that is acting as a qubit. And then that, obviously, once it's observed, it no longer exists in superposition. So it loses that quantum ability. So I think one of the final ones we're talking about, so we talk about superposition, entanglement, decoherence, interference. One of the final ones we're talking about, one of the more like complicated ones or difficult to understand ones is tunneling. So tunneling is sort of a difficult analogy to get sort of like to digest, but let's say you have a ball rolling towards a hill. Obviously, in the real world, in some sort of classical world, if the ball doesn't have enough energy to climb over the hill, it'll roll back down. Let's say the ball's like rolling up this first or second hill. If it doesn't have enough energy to make it to the top, it'll just roll back down and it'll get stuck. If it does have enough energy, it'll go over the hill and go through it. That's obviously all well and good. However, in the quantum world, the chance that the ball could tunnel through the hill and appear on the other side. The mechanics of how this tunneling works is a very sort of in-depth physics field, but you can think about just tunneling as if it doesn't have enough energy to go over the hill, it has a chance of just going through the hill instead. So in a more like scientific way, it's a phenomenon that a particle can pass through an energy barrier like a hill when it doesn't have enough energy to overcome it in a classical manner. When objects in sort of the quantum world tunnel through things, it's not like interfering, it's not touching it, it's just passing straight through it. And one of the scientists that worked on this was Hartman, and he created this effect called the Hartman effect that predicts that as a barrier gets thicker, the tunneling time doesn't increase significantly. What that means is, as let's say the wall or the hill you're going through gets thicker and thicker and thicker, it gets bigger and bigger and bigger, the time it takes to tunnel through it doesn't actually get much longer. It's a very sort of debated physics sort of field, but that's what was theorized at least. So let's say in the top is sort of a classical way of thinking about things. When you shoot a bunch of sort of light at a wall, obviously light and things can't go like through the wall. So it just bounces back or reflects back from the wall. But in the quantum mechanics world, the light can actually be able to pass through the wall and spread out on the other side. And another thing is, as the thickness of the wall varies, it doesn't change the sort of speed or the way in which the photons and the particles are able to go through that barrier. And some of the applications of this field, although they are sort of difficult to understand from a physics perspective, is stuff like nuclear fusion. So that requires these small like atomic nuclei to come close enough to like overcome the energy that's bringing them together. But quantum tunneling allows you to sort of break through the energy barrier without having energy to go through it. And there's also a few sort of innovative or pioneering technologies in imaging and measurements, like scanning tunnel microscopes, which you could read more about if you want. And they, what this how STMs work is they measure variations in current by dragging a tip across of a surface or across a particle that you want to visualize, and that it causes electrons to tunnel across them. And by measuring the current variations of the electrons, you're able to actually create a detailed service map of something. Obviously, it's a very, very complicated thing. Nobody should know much about that, but if you want to look up more things about this sort of tunneling in the future, these are two fields you can think about and research more on your own time as well. Thinking about time, I'm going to go through a few of these a little bit faster. So quantum computing algorithms are instructions designed to be executed on quantum computers. So obviously, you execute algorithms on your normal computer. There's specific quantum computing algorithms that are designed to be executed on these quantum computers. So these algorithms essentially, they take advantage of these properties of quantum computing that we mentioned before, the entanglement, superposition, decoherence, and they solve problems that are either impossible or incredibly inefficient for classical computers. Some of the properties of these algorithms are stuff like quantum gates. So in normal computers, you have like and, or, other sort of gates like that. Quantum gates are used for quantum computers. They're probabilistic, so they don't always get the correct answer with certainty. Like, let's say an addition algorithm on a classic computer will always return the right answer. A quantum computer might not be able to give that answer all the time that's right, but it'll give an answer much faster, and there's ways to manipulate the algorithm so it'll get you the output that you want. And then there's also parallelism, which we talked about before, in which it can exist in multiple states at the same time. So you can speed up processes by doing multiple things at the same time as well. So some examples of like these algorithms are, let's say, Shor's algorithm. Shor's algorithm is used in a lot of cybersecurity applications nowadays because it can take very large numbers. Let's say you take like 15, the factorization of 15 can be 5, 3, and 1, if you want to talk about prime factorization. And the way that RSA works, it's an algorithm developed by, it's an algorithm, it's a security mechanism that uses Shor's algorithm. And it's a security system that's used nowadays especially. And RSA relies on factoring very, very, very large numbers. And classical computers would probably take tens to hundreds of years to be able to crack these large number of factorizations. But quantum computers can solve them in a matter of minutes or a matter of hours. So if a sufficiently powerful quantum computer is built, it can take down the security of online transactions and data. Next thing is Grover's algorithm. Grover's algorithm is a quantum algorithm used for sorting a large unsorted database for a specific item. And the way that this can be used is, let's say you have a very large database. Let's say Google has a list of all the websites that have ever existed on the internet. You want to be able to search through it. They don't use this, and nowadays use other algorithms for this. Let's say that data is obviously unsorted. It's very difficult to search through. You want to find a specific website, do that. You can use Grover's algorithm as a way to significantly speed up that operation. And also, that can be used to optimize certain equations and also be used to attack systems. Let's be able to guess passwords or crack passwords by trying out every single combination possible in a much shorter amount of time than a typical computer would take. This is one of the parts I want to focus a little bit more on, and that's how do you actually build one of these quantum computers? What does a quantum computer look like? So this is what a typical quantum computer looks like. It looks like some sort of sci-fi technology. It looks much different from the laptop or computers you're used to seeing on a day-to-day basis. So this top part, the white part over here, is called the shell. So the shell acts as, excuse me. The shell acts like a guard from the environment. It's what prevents a lot of the decoherence we talked about before. And it shields it from a lot of different things. It keeps everything inside of it very, very cold and very, very vacuum sealed. It acts as a thermal shield, preventing it from heat from the environment, protects against light, protects against noise, protects against just general dust and dirt getting into the system as well. These cables you see like strewn apart throughout the computer are what's called nerves, similar to the way that nerves work in our actual body. These carry signals to and from the chip and throughout the entire computer as well to drive the operations and the quantum operations the computer does. The skeleton, these sort of gold plates you see throughout, are what separate these zones of the computer. Since computers obviously run very, very hot, quantum computers are no different from that. And we need to be able to cool them very efficiently as well. So we separate the computer into what's called cooling zones. And these gold plates are what separates these cooling zones individually. And inside these layers, they dip to just above absolute zero, which is very, 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 very cold. And at the bottom, they can dip to almost within 1/100th of a Kelvin, which is almost the same temperature as outer space or even colder. This middle part is what's called the heart or the mixing chamber, which is what's the core of a quantum computer. It's where the cooling happens. It's where it uses liquid helium to cool very, very quickly. And it helps reduce the force applied to keep the entire system running stably. And finally, at the bottom, we have the brain, or the quantum processing unit. This is sort of like, the CPU in your normal computer. This is a QPU for the quantum computer. That's where all the magic happens. It's where all the computational components reach a solution. It's where the algorithms are run. It's what takes advantage of all the different information stored in the nerves throughout the entire system. Let's take a look at time. So what are some of the different types of quantum computing? Now we're going to go more to, we've talked about what quantum computers are and how they work. Now we're going to talk about a little bit of what are the types of quantum computing that are available, or quantum computers that are available. So there's quantum annealers, which are very, very basic versions of quantum computers. They optimize solutions by searching over like a search space. As you can see on the right, they're not that difficult to build. And they don't have a lot of benefits over classical computing, so they're not often used, but they can be helpful for like some sort of optimization problems, but they don't have any advantages over traditional computers. Analog quantum computers contain typically around 5,200 qubits, or that's generally what we consider them to have. And these are what are used during typical quantum computing applications, stuff like quantum chemistry, material sciences, coming up with new materials, designing sort of proteins for cancer and things of that nature. This is the most sort of probable type of quantum computer. It's still difficult to build, more difficult than annealers, but this is where we're going to see our actual speed up over the next 5 to 10 years. And then the last sort of stage is universal quantum computers. These are what we want to be able to build in the very, very far future. Maybe around 100,000 qubits. This is what can break our current cryptography systems. It's what can enable that quantum internet that we were talking about before. It's a very, very high computational power, but it's also way beyond the scope of our current science applications to build good versions of these. So quantum annealers, I'm going to skip through a little bit of this, but generally they're a very specialized set of quantum computing that helps optimize problems. It basically just says, let's say you have a system that can go through, let's say, a wrong solution and a better solution. It'll keep using magnetic fields to optimize the probability that you're in the best solution possible. And so eventually the probability that you're in the best solution possible is so high that you can guarantee that the output of the problem is the solution that you want. And the programmable quantity that we are actually programming is the magnetic field within the system that, as you mentioned before, electrons spin in different ways in magnetic fields. So you're able to control the magnetic field, you're able to control which state electrons are in, and able to guide the probabilistic nature of a quantum computer to a definitive outcome. This is more information about sort of how these annealer works. You can read more about this when we provide the slides to you as well, or in the recording. But this is what's available for that. And what are some of the advantages and limitations of these quantum annealers? So the advantages are that it can find solutions faster than classical methods for certain problems, but it's a very limited problem scope, and it's ongoing debate about if there's any actual advantage of providing these over typical classic computers. So they can do problems like optimizing sort of airline routes, through traveling salesman problems, things that can be done by classical computers, but maybe done a little bit faster to the parallelization that a quantum computer provides. So next thing is sort of like analog quantum computers. These are a little bit more powerful than the annealers we were talking about before. And here, instead, they're at their early stages, but these are the ones that have the actual power to change the world and the potential to change the world. This is what a lot of companies work with nowadays. So typically around 50 to 100 qubits, and they perform a lot of the operations we were talking about through utilizing superposition, utilizing interference, utilizing entanglement to solve and understand phenomena that are too difficult or take too long for regular computers to handle. And then at the end, we have the universal quantum computers. And these are what are based on like quantum gates. They have quantum circuits. It's essentially overhauling our entire existing computing architecture to be used within a quantum system. And these tech giants like IBM and Google are working on building these computers, but they're still going to take 20 to maybe 30 years before we even get introductory stages of these computers. So what are some of the use cases and actual applications of these as well? So there's actually cloud services we can use quantum computers if you would like to. I'll just quickly skip through a lot of them, but essentially the advantages are, obviously we can't have quantum computers. They're used by mainly big companies or research organizations. But if you want to be able to take advantage of these quantum computers, you can actually write code for these sort of quantum algorithms and then send them to computers in the cloud and get the outputs back. The same way you can send information to the cloud in any sort of way. And cloud-based quantum computing is taking a lot of storm in the market because not a lot of companies or even countries have access to these computers. If you want to run algorithms on them, you can utilize pre-built computers by these big companies who are offering their services to other people through the cloud. So these are a lot of examples. Google has some, IBM has some, and there's some individual companies like small startups that are also working on these computers as well. So what are some of the development tools? Like I was mentioning before, there are certain like quantum development languages, quantum development kits as well. A lot of this information you can look through the slides as well, but obviously when you're dealing with quantum computers, there's different languages, different sort of frameworks you have to work in. And so there's different languages as well. One of the very, very popular ones is called Q#. It's done by Microsoft, and it works with their sort of the Microsoft Cloud services, and it's similar to their other Microsoft language called C#. And it's utilizing a familiar sort of architecture to work on quantum computers as well. And if you want to learn more about some of the quantum properties of Microsoft and Microsoft Cloud, you can go to quantum.microsoft.com or look at Azure, which is Microsoft's cloud service. Another one of them is IBM. So we mentioned IBM a lot, and IBM is a very, very, very popular company. And obviously they're working on quantum computers as well. They've also taken their own sort of step into the quantum cloud realm as well. So these are more sort of quantum tools and quantum projects. And in the future, what are sort of applications of quantum computing? Like we mentioned before, they have applications in artificial intelligence. Being able to execute large, complex processes in a very short amount of time is very helpful for training large models. They have applications in like drug design, so you're able to theorize all the different possible combinations and outcomes of a drug, of a medicine. You're able to create medicine much faster to solve much more complex problems, like even cancer potentially. Cybersecurity, like we mentioned before, being able to crack very, very large numbers and very large codes very quickly. Financial modeling with like stocks in the market, there's a lot of different things to consider. The more things you can handle at once, the better your models will be. And things like weather forecasting as well, because you can take in so much more input and analyze it much quicker. So you can have much better reasoning and output towards saving lives and predicting natural disasters as well. So with that, I think I'll call the sort of presentation there. I want to take some time for questions and look at any sort of questions that I have possible. So let me see if there's any sort of questions here. All right, yeah, so all of the recordings will be available, and I'll also provide these slides as well towards the end of the program. I know we didn't get to go through all of it, but there's a lot of information in quantum computing, and I try compressing it as much as possible. But there's even more information out there than this provide. Someone asked me, would increasing the number of qubits increase the rate of decoherence? Yes, since the more and more qubits that you have a more and more chance of those qubits being interacting with the environment, and thus increase the rate of decoherence much higher. That's what the issue with building quantum computers is. The more and more qubits you have, the more and more difficult it becomes to keep them all stable, keep them all running at once. That was a good question, though. Does anyone else also have any questions before we sort of conclude the program? Yeah, there will be slides for like high school resources and stuff coming up as well in the future weeks as well. If there's not any other questions, then I'll end the presentation here. We have another presentation coming up about like sort of medical careers in medicine, and hope you enjoyed. And we'll provide the slides and recording to everyone else as well. Thank you so much. Hey everyone, I wanted to give a quick addendum to the recording because we didn't get to go through all the slides. So I'll get started from where we left off initially. So where we left off was we were talking about what are the applications of quantum computing. We're talking a little bit about the cloud, how you can actually use quantum computers in the cloud. Now a little bit about like the applications. We're talking about cryptography. Specifically, RSA cryptography is the biggest sort of use case of quantum computing and cryptography. This like I mentioned before, involves factorizing numbers. Let's say factorizing 15 into 5, 3, and 1 is a very quick process. But factoring, let's say, a 40-digit number, 50-digit number, 60-digit number, starts to get in the order of minutes, seconds, or even hours and days, the larger and larger the number gets. And RSA, the cryptography system that uses, is a very highly used cryptography system nowadays. It uses what's called a private key and a public key, and performs encryption and encryption using those public key and the private key. Private key is what's held by the bank or the secure system. Public key is what you share to get your information out towards others. And the larger and larger the prime numbers you do this encryption with, the better, the stronger the encryption is. Now, classical computers can't really factorize these numbers once they get past maybe like 100, 200, 300 digits. Quantum computers are very, very good at this factorization problem. They're able to do it very fast, do the parallel operations, and therefore they have a large strength when it comes to quantum computing. It's also very dangerous because if quantum computers can break the RSA encryption, our big public and private key encryption, then that poses a large danger towards, hey, if we can't use that anymore, if Google or IBM or any with a quantum computer can break those encryption softwares, then they could get access to a lot of confidential information and break a lot of like secure systems like banking and stuff as well. But obviously, there's a lot of complexity come implementing them, the cost of the hardware it takes, and limited distance for communication that comes with that sort of quantum cryptography as well. So a little bit more about like some industry sort of stuff with the quantum computing. Some of the notable scientists who've worked on quantum computing are Benioff, who developed the sort of first mechanical model or quantum model of a Turing machine, which is a baseline for quantum computing. Feynman, who, if you've taken physics classes before, I'm sure you've heard of him. And he was awarded a Nobel Prize in Physics, actually, for his development into the world of like quantum computing and not quantum computing, but like quantum physics and quantum dynamics of electrons and stuff. Deutsch, who also worked on quantum Turing machines and developing a first model of the universal quantum computer that we talked about. And he's typically considered the father of quantum computing. Some of the history of quantum computers at a glance. As you can see, the history pretty much only starts in 2017, so very, very, very recent. We started with 2048 qubits for quantum annealing, which, as we mentioned, is a very, very low power system, and it's one that only can be used for some sort of optimization problems, not a lot of like large scale use cases like cryptography and things of that nature. Then IBM started with 50 qubits, and slowly but surely we've been building on more and more and more quantum computers. And as of 2023, IBM has 433 qubits of an analog quantum computer, and that's typically considered the quantum supremacy because for specific problems, they proved that their computer does it faster than any other computer out there. There's a lot of history that comes with quantum computing. Like, it's a very modern field in terms of the applications of it, but the actual theoretical nature of it starts all the way back in 1973 when people first theorized that, hey, you could have qubits, you could store information in these electrons that have both positive and that both have up and down spin without us observing them. And then as obviously once the 2010s and the 21st century start to roll around, started getting more and more practical implications and stuff like companies like D-Wave and IBM and Google have been sort of pioneering the field as they go forward. And this might actually come as a shock to a lot of you, but you can actually work on quantum computing as a high schooler. It might seem like a very far off, very research, very PhD person field. It's actually a field you can get your first introduction to if it really interests you in high school. There's a lot of programs that we have about sort of quantum computing, working on quantum annealers and stuff as well. University of Chicago has a program called Quantum Quick Start. Miami University, Missouri University, Brown University, all these different programs have opportunities for you to actually work with researchers in quantum computing, actually work on quantum software and quantum computers. It's a very, very sort of niche field. You can really get an edge towards like your college applications, or if you want to work in this field, you can really get an edge on other people in the field as well, and get a nice introduction to it. This is actually the world and the physics and the realm that I actually want to be working in. Here's some more sort of programs about quantum computing, and they sort of bridge the gap between some being more physics and theory oriented, some being more engineering oriented, like how do you build the quantum computers. Other ones are how do you write software and code and actual computing algorithms to actually work on these quantum computers. So all facets, from the theory to the engineering to the development, have individual roles and places for you to go and explore and work with. here are some of the schools that are really pioneering the research in quantum computing. Caltech and MIT. Caltech especially has done a lot of work with quantum computing. A lot of quantum computing professors, researchers are tenured there. Obviously, a lot of the big schools work on quantum computing, the big technical schools, and also schools like University of Chicago, University of Colorado Boulder, and UC Santa Barbara have very, very strong quantum computing programs relative to their general like computer science programs as well. So if you're interested in research at universities where they have a strong history in working on quantum computing and really pioneering researchers and professors working there, here's some sort of choices you can take a look at when you're applying towards colleges as well. And if you're familiar with hackathons, which hackathons, for those of you who are not familiar with them, are programs where either virtually or in person go and spend maybe 12 hours, 24 hours, 36 hours, and you give it a set time span, which you can complete any sort of project related to the theme that you want. Typically, hackathons are themes like education technology, using certain Google software, working towards this sort of theme. There's like hackathons for companies like make the next like Spotify feature. And in this sort of line, I thought we have quantum computing hackathons as well, which are free for anyone to join, free for anyone to participate in. Typically give you credits. So if you want to work with quantum computers in the cloud, they'll give you the credits to work with that. And you actually just spend a few hours, spend a few days just tackling a problem in quantum computing and really get your hands dirty with what it means to work on these sort of systems. You get a good introduction to them as well, while maybe potentially winning some prizes along the way. And that should be all for the slides. And as always, if you have any sort of questions, obviously this recording is live information. You can pause, rewind, do whatever you want. But feel free to reach out to like me or the Aegis Navigator team as well with any questions you have. We'll be glad to answer them as well. Thank you so much, and hope you have a great day.